If you've ever sat down with a pencil and a printout of a dam cross-section to draw a flow net, you've engaged in a silent dialogue with one of history's greatest mathematical minds. Those neat, curvilinear squares aren't just a clever drafting trick. They are a graphical solution to a profound physical truth. Every time you ensure your flow lines and equipotential lines cross at right angles, you are manually approximating a solution to the Laplace equation. This mathematical powerhouse governs everything from gravity to heat, but in the world of civil engineering, it's the secret sauce behind how water moves through soil. The Newton of France. To understand the math, you have to understand the man, Pierre-Simon Laplace. Rising to prominence in late 18th century France, Laplace was often called the Newton of France. He was a man of staggering ambition and intellect who survived the French Revolution and the volatile ego of Napoleon Bonaparte by making himself indispensable. While he is famous for his work on celestial mechanics and probability, his most enduring gift to the physical sciences was a deceptively simple second-order partial differential equation. It was designed to describe the potential fields of the universe, but it turned out to be the perfect language for seepage. The elegance of the equation. At its core, the Laplace equation, written as del squared phi equals 0, represents a state of equilibrium. In the context of groundwater, it assumes that the fluid is incompressible and the soil is isotropic, meaning it behaves the same in all directions. The equation essentially says that there is no net source, or sink, of water within the soil mass. What goes in must come out. It describes a smooth, continuous distribution of energy, or head, across a medium. When you draw a flow net, you are visualizing this equilibrium, mapping out how potential energy dissipates as water fights its way through the pores of the earth. From calculus to the drafting table. Before computers, solving del squared phi equals 0 for complex boundaries, like a cofferdam or a levee with a tow drain, was a mathematical nightmare. Engineers couldn't always find a closed-form solution, a clean formula, for every weirdly shaped foundation. This led to the development of the graphical method. By following a strict set of geometric rules, maintaining curvilinear squares, engineers realized they could solve Laplace's complex calculus using nothing more than spatial intuition and a steady hand. The flow net became the analog computer of the 19th and 20th centuries. The stakes of the solution. Why does this history matter to an engineer today? Because Laplace's equation tells you where the danger lies. When those squares in your flow net get smaller and more crowded near the exit point of a dam, the equation is screaming at you that the hydraulic gradient is spiking. This is where piping or boiling occurs, the literal internal erosion that can cause a multi-million-dollar structure to collapse. Laplace provided the framework to predict these failures long before we had the sensors to monitor them in real time. A legacy in every line. Today, we mostly let finite element software handle the heavy lifting, crunching the Laplace equation in milliseconds. However, the intuition gained from a hand-drawn flow net remains irreplaceable. It forces you to feel the flow and respect the balance of forces that Laplace identified over 2 centuries ago. So, the next time you look at a grid of water moving under a structure, remember the French polymath who looked at the stars and saw the same patterns of equilibrium that prevent our dams from washing away.